To begin with, we study vectors from a geometric point of view. If we talk about a position vector, we are taking the one special case where we put the tail of the vector at the origin. That tip of the vector ends up at some location A, B, C, and the coordinates of the point are exactly the same as the components of the vector. That allows us to make the following interpretation. Vectors are points in R3. You can then extend and then talk about collections of vectors. We're going to talk about a very special case to begin with, every single multiple of a single vector v. Now this t right here is called a parameter. And what that means is it's a number. You can set it to be anything you want. That means R is actually infinitely many different vectors. So for example, it includes 0v, 1v, 2v, and it can go up as far as you'd like. You can have negative 1v, negative 2v, and as far as you'd like. You could take fractional multiples of v. You could even take irrational multiples of v. So you could have e times v or pi times v. And this nice formula collects them all. What we're interested in is whether there's some sort of geometric pattern with this collection of vectors. And in fact, there is going to be, and it's best understood if we visualize things. Here's the vector v. You could imagine another vector that's twice as long. So there's a 2v, and here would be a 3v. And remember, we're interpreting a vector as a single point. Down here would be a negative v. This would be 0v. This would be 1/2 of v. And if we take more and more and more multiples, all of these infinitely many points organize themselves as a line that goes through the origin in the direction of v. This line extends out to infinity. The larger I take that number in front of the v, the further out I push the vector. R is the position vector of some point along the line. You set the dial of t, it's going to produce a vector r that lives somewhere there. The bigger you make the t, the further out the r goes. The more negative you make the t, the r will switch direction. What would happen if I added some sort of constant vector? What pattern does this produce? As always, we're going to build our 3D coordinate system. Here is the vector v, and let's take this to be the vector r0. So if we let t equal to 0, then what this formula produces is simply the vector r0. If I let t equal to 1, then what I'll get is an r0 plus a v. So if I think about the parallelogram rule, what this is an instruction for how to add those two vectors. And the result will end up being right here, r0 plus v. Now, if I continue doing this, I'll get different additions. And if I were to stretch out the vector to 2v, and if I were to use the parallelogram rule again, what I would find is another vector right there. I could extend it to the negative direction, so there would be negative v. And if I were to use the parallelogram rule here, this would be r0 minus v. So if I kept playing this game over and over and over and over again, what I would find is a new pattern. What this recipe produces is a shifted line. And this is a line that goes through no longer the origin. The origin has been moved up to r0. So it goes through r0 and it's in the direction of v. Another application of vector notation is related to linear equations. In particular, let's talk about a linear equation with 3 variables. We'll call it x1, x2, and x3. Now, we encountered these when we solved systems of linear equations. We're going to let a solution to this equation be given in this vector form, and then we'll ask, do the solutions to this equation form some sort of geometric pattern? If we were to take the solution set and somehow organize them in a geometric way, what would we see? Now note, if we just had these 3 variables and there was no constraint on them, then x1, x2, and x3 would all be what we call free variables. They could all be free to be chosen as some real number. But the equation that we've been given offers some sort of constraint on one of those variables. If we were to take this equation and solve for, let's say, x1, what we would find is that x1 is not free. x1 is connected to the values of x2 and x3. Now, because of that, if we were to take this same vector that holds all our solution components and we were to sub in this constraint, what we would find is something interesting. If we were to rewrite this slightly, we could have a 1x2 and a 0x3 in that second component, and we would have a 0x2 and a 1x3 in that third component. Now notice that we're not really changing anything here. All we're doing is adding extra zero forms. Now, why would we do that? Because of vector properties, what we can now do is split this up as a sum of two vectors. Now, we're used to typically taking two vectors and combining them into one, but there's no reason why we can't go backward. So we are going to take this one vector and write it as a sum of two. Now, another vector property says that if each component in your vector has a common multiple, we can factor out that common multiple. What this does is it now allows this to be written as follows. So the points that form all of the solutions to this equation can be written as follows. We're going to call this vector u, and we'll call this vector v. The solutions to this scalar equation must have this form. x2 and x3 are free. They can be any numbers we'd like. The scalar equation doesn't impose any constraints on them. Now realize I could have solved that linear equation for either x1 or x2 or x3. It doesn't matter. One of the variables can always be isolated, and it's always going to be in terms of the other two. What this does is it forms what we call a linear combination. Now, in the next set of videos, we'll talk a lot more about what a linear combination is. All the solutions to that original linear equation look like this. I would like to visualize this. The vector u is 3, 1, 0. The vector v is 5, 0, 1. These two vectors are not multiples, and that means they are not going to be on the same line. We could take our three-dimensional coordinate system, something like that, and we would have the vector u somehow like this and a vector v somehow like this. And what we're going to do is adjust these numbers in the front. These are called weights, and we can weight each of these vectors more heavily or lightly depending on the values we choose. For example, if I wanted to choose one bunch of u and 0 bunches of v, that would take me right here. If I wanted to take 0 bunches of u and 1 bunch of v, that would simply be this vector. I could take 0 bunches of u and 0 bunches of v. That would just get me to the origin. But now we're going to make it a little more interesting by taking 1 bunch of u and 1 bunch of v. According to the parallelogram rule, this is going to produce a new vector that lives right here, u plus v. Now, I don't have to stop there. I could take 1 bunch of u and 2 bunches of v, so that would take me out somewhere over here. I could take negative bunches of these vectors. So I could have 1u subtract 1v. So this would take me out somewhere over here. And if I were to take every possible multiple of the first vector along with every possible multiple of that second vector, what we would find is that there would be a pattern. This would create what's called a plane in R3. So a plane is essentially a sheet of paper. Now this sheet of paper is infinite. It goes forever and ever and ever in certain directions. And the two vectors that we used to form this plane are the u and the v. The equation that we found earlier, so this is called the scalar equation of this plane, is exactly like the equations we see when we solve linear systems. But there's this second version. There's this vector version. And the vector version says, I'm going to tell you the points on the plane. They are going to be some multiple of u and some multiple of v. Both of these versions of the equation of the plane are equivalent. Any scalar equation that looks like this, so anything that we see when we solve a system of linear equations, will always lead us to some sort of vector equation that looks like this. The vector form allows us to gain geometric intuition. It's important to note that this plane contains the zero vector. It contains the solution 0, 0, 0. 0, 0, 0 is a solution to the scalar form of the equation. It satisfies this equation and geometrically means that this plane must contain the origin. Now we can change things just like we did with the line. Let's put a non-zero number there on the other side of the equation. Which points satisfy this equation? As before, we're going to use our new vector notation to write things down. We are going to treat this scalar equation as a constraint equation. We're going to pick one of the variables to solve for. It doesn't matter which one. Here I'm picking x1 because it's convenient. And then I'm going to sub it in to this equation here. x1, x2, x3. I'm just going to replace the x1 with this expression, and then I will have the x2 and the x3 as before. Now I'm going to use the same vector property idea. I'm going to now add in some zero terms into all of these second components and the third components, and I'm going to be clever about how I write them. I'm trying to come up with a pattern. If I were to use the vector properties like I did earlier, what I can do is split this up now into 3 vectors. x2 will be the weight in front of the first one, x3 will be the weight in front of the second one, and now the last one won't have any weights at all. I will call this u, I will call this v just like before, and I'm now going to call this some other point p. The scalar form of the linear equation tells us which points will satisfy that equation. Geometrically, we think about it in vector form, and in vector form, it tells us those same points must satisfy this pattern. As before, the x2 and the x3 are free. They can be any number we want. So if we wanted to try to visualize this, if I were to set x2 and x3 equal to 0, that means one point on the plane has to be this vector p. So the origin essentially gets shifted to this new point p. And those two vectors that we had before, u and v, they created a plane down here. If I were to use parallelogram rule and take any point on the plane, that plane is now going to get shifted up to here. And so what ends up happening is I now get a shifted plane. When I have a scalar equation that has 3 variables like this, and there's a non-zero number on the right-hand side, this is going to lead to a vector form that looks something like this. Remember, the scalar equation tells us which coordinates, x1, x2, x3, will make this equation true. But if we want to think about it geometrically, what that's going to do is give us a plane that has been shifted off the origin. The origin now becomes this point P, and the entire plane just moves up. Anytime we solve a system of linear equations like this, we can interpret each equation as a shifted plane.